Hello and welcome to day 11 of the 12 projects of Codemas. My name is Astronaut. I am a Linux sysadmin, and let's go ahead and get right on into it. All right, day 11 unboxing. Almost done. Looks like we've got 4 more mel-to-mel jumper wires and a pre-soldered 0.96-inch OLED 12C display. Maker Advent Calendar Day 11. OMG OLED. Welcome to Day 11 of your 12 Projects of Codemas Advent Calendar. Today we're playing with a really fun and useful component that you'll use again and again in your projects. A mini I2C OLED display. I think that's an I. While only teeny tiny, these little displays are great for showing data from your project, such as sensor readings, scores, pin status, alerts, and other useful information. We're going to combine it with some components from earlier boxes to show you just how handy these are. Let's go. Box 11 contents, as we saw, was the pre-soldered OLED display and 4 more mel jumper wires. Today's project, we're going to display data on our mini I2C OLED display. They're relatively easy to code, but they do require the installation of a library, which we import at the start of our program, but we'll guide you through this. What is an OLED? Okay, it is I2C. Sorry. What is an OLED? The display in your box is an OLED display. OLED stands for Organic Light Emitting Diode. You may have seen these mentioned on advertisements for TVs, as many models use this technology. It's a type of digital display technology that uses LEDs and layers of thin organic film between 2 electrodes. When electrical current is applied, the display emits light. Our code tells the display where to show light and when. What is I2C? Sometimes referred to as IIC, stands for Inter-Integrated Circuit. It's another type of communication protocol. Remember one wire from day 8, which allows multiple I2C devices to communicate to a controller like our Pico. I2C requires just 2 wires to communicate, along with 3.3 volt and ground for our display. And it has benefits over some other communication options, but we won't bore you with that just now, as it's not going to be relevant until you're much further along on your maker journey. To use I2C, we need to import it in our code, which we'll show you in just 2 ticks. Construct the circuit. First, disconnect your Raspberry Pi Pico from your PC, ensuring it's powered down. Today, we're finally removing the LEDs and buzzer as input components, like buttons and sensors, are more relevant and useful with this display. If you haven't already, remove everything so that you're back to a clean breadboard with just your Pico fitted, like this. All right. Alright, back to the Pico. Next, fit one of your buttons in the OLED display into the breadboard like we have below. Make sure you leave a gap above both for us to add our jumper wires. Next, we'll add our 3.3 volt connections. Run a jumper wire from the 3.3 volt pin, or physical pin 36, to the upper red channel. Then connect the left button pin to the same red channel, and the second OLED pin labeled VCC to the same channel as well, like below. Next is our ground pin. Connect the first OLED pin labeled ground to the nearest ground pin on physical pin 18, like we have below. Now for the 3 GPIO pins, which will talk to our Pico. Connect the right button leg to GPIO 8 or physical pin 11. Connect the third OLED pin labeled SCL to GPIO 1 or physical pin 2, and connect the fourth OLED pin labeled SDA to GPIO 0 or physical pin 1. We'll be using the light sensor from box number 6 in our examples today, so we need to wire that up as well. We'll use our mini breadboard for this. Fit the light sensor and the 10K resistor into the breadboard as we have below. The long leg of the light sensor needs to go to the left. Now to wire up the light sensor to our Pico. Connect the left resistor leg to the ground connection on physical pin 28. Connect the left light sensor leg between the leg and the resistor to GPIO 26 or physical pin 31. Connect the right light sensor leg to 3.3 volts on physical pin 36. All right, I think this is right, but we'll see. Now turn your breadboard 90 degrees so that the OLED is facing you. This will make it easier to read and view and read the text we show on it. Install code libraries. Plug your Pico back into your computer's USB port and make sure it's recognized. Then let's install what we need to make this display work. Our display needs a code library package that isn't included in MicroPython by default, so we need to install that before we can start using this display. We will then import this library when we write our code. Luckily, this is very easy to do and all handled within Thani, so let's get it installed. The following may vary slightly depending on the type of computer you're using. Important: if the steps below don't work for you and you see certificate errors or other similar messages, you may need to install the library manually. Alright, in Thani, from the top menu bar, select Tools, Manage Packages. You should see something similar to the box below. Tools, Manage Packages. Activity 1, Simple Text Display. We'll start by showing a single line of text on the display to kick things off. Of course, it'll be the traditional Hello World. I2C and Display Setup. To use this display, we need to import I2C as well as the library we just installed. You'll see this in the first few lines along with other imports as always. We need to set up I2C and the display, which you'll see on line 7. This includes the GPIO pins we're using, GPIO 0 and 1, which are the SDA and SCL pins used for I2C connections. After this line, we always have to wait around 1 second, otherwise I2C can get all stroppy and fall over. Next, we define the display size in pixels and the type of driver chip it uses. Our display uses an SSD 1306 driver, and it is 128 by 32 pixels, which is reflected on line 13. That's all the setup out of the way, displaying text. When we want to display something on the display, we always go through the same process. Clear the display, define what content we want to show on the display, and then push the content to the display. If we don't clear the display every time, it will write new content on top of the old content, which makes a big mess of jumbled up characters. Not good. Our example shows us clearing the display with display.fill0, then sending hello world with display.text hello world, and finally pushing this to the display with display.show. The code. We'll cover what the 00 arguments do in the next activity, but for now, copy this over to Thani and see it for yourself. All right, fingers crossed. All right, sweet. Looks like it worked. Activity 2, multiple lines of text. Let's go one step further, adding more lines and changing the position of the text. But first, let's cover those arguments. You'll notice that there are some arguments after the text we push to the display. Display.text hello world, 0, 0. The first argument determines how many pixels across the display the content should start, the x-axis, and the second argument defines how many pixels from the top the content should start, or the y-axis, going downwards. Our display is 128 by 32 pixels, so we have 128 pixels running across the x-axis and 32 pixels top to bottom on the y-axis. In our example below, we've managed to squeeze 3 lines of text on by setting each one at a different height, which just takes a bit of trial and error. The first line is at 0, the second line starts at 12, and the final line starts at 24. If we add more lines, they won't be fully visible. We've also moved line 2 over to the right by entering 50 for the first argument. Then, again, just with trial and error. Give the example below a try and then have a play with the argument values to see the changes for yourself. All right. All right, sweet. Activity 3, the endless counter. Small OLED displays are great for displaying data, and they can refresh quickly enough to show data changes at a very fast rate. Let's create an endless, counter to show another way of using these displays. When you come to make your own projects, things like this will be very useful. We don't use any physical inputs here, just a counter in our code that increases by +1 every loop. The code. A new problem. Our counter is a number, or an integer, but our fussy little display will only show text, which is a string. So we need to convert our counter to a string every time we run the loop, converting integers to strings. We convert the counter integer to a text string using the following line: display.text string counter 024. So instead of entering the text in brackets or parentheses, like we did in the previous activity, we use string counter to turn our counter variable into a string for our display. It's otherwise quite straightforward, adding +1 to our counter at the end of every loop to continually increase it. You can play with the time delay within the while loop to see just how fast it can run. All right, so let's go to the next activity. Activity 4, the naughty or nice game. We're now going to create a game that decides your festive fate. Let's make a naughty or nice game which will tell you if you're on the good list this year or not. Don't worry kids, it's just a bit of fun. We're sure you've all been good this year. The project shows naughty and nice with a marker that very quickly switches between the two. When you click the button, it stops on whatever option the marker is on at the moment. Your aim is to land on nice. The code. Our example below uses all our usual ingredients: imports, display setup, button pins, and creates a state variable, which we've used before. We use this variable to switch between the two if statements within our while loop. But why do we want to do that? We want our display to constantly move the greater than marker between naughty and nice. To do that, we have two if statements, which are triggered by our state variable being either 0 or 1. Each if statement starts by showing the text with the marker at a different position. If the state is 0, the text pushed to the display shows the marker on naughty. If the state is 1, the marker is on nice. Each if statement also changes the state so that on the next loop, the other if statement will trigger, making the marker jump between the two. Each of the if statements then has a nested if statement inside it, which checks if the button is pressed at that very moment. If it is, the code inside it updates the display to confirm which option was selected, followed by a 2-second pause. All right. All right, so we set everything up. State 0, all true, state equals 0. Okay, so if the button's on 1, or if naughty is the one that is selected, and you press the button, then you get this "oh no" text. The state is 1, and nice is selected, and you press the button, then it says yay. All right. All right, so that time we got nice. That time we got naughty. Activity 5. Show me the light. Showing sensor readings on your OLED is quite possibly one of the most useful and fun ways to put the display to good use. We're going to run an example where we continually check the light sensor reading and push this to this display. It can even show the % symbol. The example below includes similar code from the light sensor box, day 6, and the same OLED display code and approach we've taken above, so most of this should make sense if you've been following along. The code. The same initial OLED imports and setup code is present, and we've added the light sensor pin setup back in, linking it to GPIO 26 along with the required ADC import. We then start a while loop, which takes a reading from the sensor on line 25. Now this line does a lot of things at once, so let's break it down. It creates a variable called light, it takes a sensor reading, it turns the reading into a percentage, it rounds the reading percentage to 1 decimal place. We did something similar on day 6, but this time we're doing everything in a single line of code. We've avoided this so far as it can be a little overwhelming, but we're on day 11, so we think you'll be okay. We then push this data to our display. We use the first line of the display to show some simple text and the second line to show the reading. Just like the previous examples, we have to convert our light variable to a string and allow the display to use it. We also added the % symbol to the end. Copy the below code over to Thani and give it a go. Alright, so let's see. Setting everything up. Alright, so we see it's around 6%. If I get my flashlight and beam it on it, then it goes up to 96%. Alright, so I guess we wired everything up correctly. Okay. So we're reading the light sensor, and then we're doing that conversion that we did to 1 decimal place. And then rounding it. Alright, sweet. Day 11 complete. Aren't OLED displays just bags of fun? We've only just scratched the surface as well. There are lots of clever ways you can use these kinds of displays with graphics, fonts, and other tricks, but we wanted to keep our activities relatively simple for beginners. You'll find a ton of resources and other examples on the internet that you can use. We even have our own graphics tutorial which can apply to these displays too, with a few tweaks to the code. Let's recap. What did we learn on day 11? Today we learned how to wire an OLED to our Raspberry Pi Pico, introduced the I2C communication protocol, learned how to install packages in Thani, learned how to code an I2C OLED display, including how to write text to the display, how to write multiple lines of text, how to alter the position of text, how to display sensor data on OLED displays, and a few little tricks like markers. Reuse knowledge and components from previous boxes such as state variables, converting integers to strings, nested if statements, light sensors, and more. Okay folks, we're nearly at the end of our 12 days. You can remove the circuit from today as tomorrow is an entirely different kind of component. We can't wait. See you tomorrow. As always, thank you for watching. Come back tomorrow for our last day, day 12.